saying that today is the first day I had 0 students to show up to either class. Not a single person came. I don't know. I assume it's because it's the last class before fall break and they just turned in that project, so they're all just kind of skipping out. But that was...
Well, you guys get prizes. Yes, hand them out.
It's kind of incredible how, you'll get like 2 to 3 weeks for a project and you'll get 0 questions about the project. And I made mine due a little bit later than those classes.
I had
Mine's due on Friday, and so I'm starting to get questions now.
Well, see, I was going to say I had the unfortunate privilege of getting assigned the.
Welcome. I've seen these before.
This is leftovers.
Yes.
Very nice.
There you go.
Wow.
Interesting.
So yeah, I was assigned the last office or one of the office hours on Thursday for the group
I'll
office
just set
hours
it down over here.
and that project review. And so last Thursday there was 3 grad students there running it, and over 40 students showed up all asking about the project.
Oh my
It
God,
was just impossible. I basically spent the whole time assigning people to rooms and then
that's incredible.
doing nothing.
Oh, can you, there you go for a second? Yes.
I want to use them so badly right now, but.
Or you can get one of those like jittery, those copies.
Yeah, sure.
You guys are +7. Oh, wait, oh. Can you go over? People, please stop by up here. This is for you. Thank you. Zach. See, baby. These are from the meeting on the weekend. Fresh. Soon.
Yeah, I appreciate the safety precautions.
Oh, yes. I use a hand sanitizer. Okay, we should probably start. Go for it today. All right, so we are looking at translations. Let me review a little bit. So last time we had the following picture. So let's say I have 2 weights over here. And let's say they're on the same facet. Namely, they have the same stabilizer under the action real-time file. So you have a picture like this, or you're in one of these places where they're like that, like on the interior. Right? So the theorem that we proved was that if lambda and mu are on the same set, then B lambda and B mu the blocks are equal for you. And the equivalence is given by the translation functors. Okay. So I'll just say by the translation functors. Right, so today what we're gonna do is we're gonna look at the situation where we have a weight which is like in an alcove and a weight which is on there like a wall. And we're gonna see what happens under translation in that situation. All right. So the first thing I want to do is I want to give a description the translation of HI of W dot lambda. And so I'm going to take all these higher sheep comb, all these B modules, and I'm going to describe what happens to the translation on these. Okay. Now I'm not going to be able to sort of do this if I am coming off of the wall, but if I'm going onto the wall, then we actually can describe this. All right, so the first thing we should do is we should analyze the translation problem. So let's look at T lambda mu of HI of W dot lambda. All right, so what is this going to be? So this is PR mu of L mu1 tensor. Well, let me just write it out. So it's PR lambda HI of W dot lambda. But the thing is, this module already has all its composition factors in the block B lambda. So we can just get rid of the PR. So this is PR mu, L mu1, tensor HI of W dot lambda. Okay. Now, recall what this was. This was RI induction from B to G of W dot lambda. So what I can do is I can use the tensor identity to move things inside. So this is the same as PR mu of RI induction from B to G of L mu1 tensor W dot lambda. All right. Now what we're going to do is we're going to look at this module here, and we're going to sort of find a filtration of this by B modules. Okay. So we take a composition series. So B composition series of this module, L mu1 tensor W dot lambda. Okay, so what we can do is, because B, remember B lowers weights. Okay, so we can take the top weight mu1 tensor W dot lambda as the sort of top composition factor, and then we can make all the composition factors go down. Okay. So we can get a series which looks like this. So we have M0, M1, all the way up to MR. And MR is, of course, the module itself. Okay. And each successive quotient is a one-dimensional representation. So MJ over MJ minus 1 is isomorphic to lambda J plus W dot lambda. There's a penalty for coming late. You have to come up here. Sorry. Just come up for a second. Just kidding, of course. There's actually a reward for coming to class. So here you go. Oh, thank you. Okay, there you go. All right. I want to make sure I get it. I actually it'll be distributed. So I don't want anyone to leave without having. Okay, so this is what happens, and we can order these such that we actually go down. So we have that lambda j is less than the partial order of lambda j prime. Implies that j is less than j1. So we can sort of make them go down. All right, now for each successive quotient over here, we get a short exact sequence. So let's analyze that next. All right, so consider the short exact sequence. 0, mj minus 1, mj over mj minus 1, 0. Okay, so remember, this is one dimensional and this is mj, this is its quotient. Okay? And now, when I apply the HIs, I get the following. So I get long exact sequence. And it looks something like this: 0. Well, there's no 0. 0 is way over. It's a long one, right? So it's a PR mu HI, okay, mj minus 1 PR mu HI of mj PR mu HI of the quotient. Okay, and it keeps on going. All right, good. Now the thing is, we can't say this is just sort of general sort of stuff. So what we want to do is we sort of want to take particular situations where there's a lot of vanishing that's going on. So for example, if there's a lot of vanishing along this column over here, or sort of these terms, then we can say more. Okay. So there are two observations I want to make. So the first observation is if you take P R of I of lambda j plus W dot lambda. Well, so if you're taking things over here, then in order for this to actually be non-zero, this has to be linked to mu. All right. So it's 0 if lambda j plus W dot lambda is not linked to mu. Okay. And if it's linked to mu, then we know all the composition factors are also linked to mu too, by strong linkage, right? So this is going to be equal to Hj of what? Yeah, of lambda j plus W dot lambda when lambda j plus W dot lambda is in WP dot. Okay, so we have control over the last term. We actually can compute it out given this setup. Okay, so that's the first thing. And then there's one other thing I wanted to mention. And that's the following. That's the following bullet point that so PR view of HI MR, okay, is T lambda mu HI W. So this is kind of obvious. So we just take this last term, applying RI induction from B to G on that, and that's just going to be this over here. Okay. tensor by those. So you just have to use the isomorphism I gave you, and this comes out sort of as an immediate consequence. Okay, any questions on this? All right, so now I'll kind of present a cool application of this. So
Sorry, just to make sure, in this,
Yeah.
projection down here, are equal eyes in the HIs?
no, sorry, this is an AHI. Yeah. This is definitely an I, and that's an I too. Okay, with the lambdas, they're J's. Thanks for pointing that out. All right, so let me present this. This is kind of a cool result. So here's the theorem. I think it's nice. So again, let lambda mu be in CZ bar. Okay. And F be a facet, okay, with lambda in it. Okay, so let me draw you a picture. So I'll draw it quite big. All right, so lambda's in some sort of facet. Let's say it's just lambda. It's in the sort of alpha over here. It's kind of hard to draw like 3 and 4 dimensions. You can kind of imagine. Right? All right, now we know what happens if mu is actually inside of here. There's just an equivalence of categories. Now, what happens when I have mu over here? Okay, so if mu is an enclosure, it's an enclosure of the set, then if I take T lambda mu on this HI of W dot lambda, okay, then I just get HI of W applied to V. And this is for all W and WV. Okay, does that make sense? So your other weights, your W dot lambdas will be higher up, or it could be anywhere along here. So I mean, you could take one across here, for example. So you would have to sort of look at, let me draw a better picture, kind of give you the idea. Let me erase this. So let's take the typical A2 picture over here. Okay, so here's this. Here's a reflection, something like this, right? Okay, so there's your picture. Okay. So let's say I could just pick my lambda to be over here and my mu to be over there. Okay. Now I can reflect across the lowest wall, this wall over here. And so I can get like W dot lambda here. And then when I reflect over here, I get W dot mu. Okay. So if I translate, let's just do an example. So if I translate H0 lambda here, under the translation, where does this go to? Under this theorem. Anyone?
Just H0 mu.
Okay, but what is H0 mu here? Non-zero or zero? What do the dominant weights look like? They're sort of inside of this, right? Right. So let me just draw that. Okay, so let me put the zero weight down here, just to make it clear. So I just want to give you a feel for like how this actually works. Okay, so the point is that the mu is outside the dominant region, so H0, 0, 0. So it does go to H0 mu here. That's going to be 0. Okay? But up here, notice what happens. So this one takes like H0 W dot lambda, so this is dominant. And this is going to go to H0 W dot mu, which of course is non-zero because it's in the dominant region. Okay? And then now, you can sort of just reflect, right? So so let's see, what's the way? So I guess we should reflect maybe over here. Like if you take this codimension one thing, you get, well, you see what I'm saying? If you reflect across here, this stays in place. Okay, so it's not like you're always going up in terms of where the closures are. You have to kind of really look at, how the affine Wildberg is sort of flipping you in various ways. Does that make sense? So for example, if I go here, I'll go here, and then I'm going to flip and I'll go outside the region. And then if I take the translation functor, I'll go get to 0. Okay, so it's still a nice result because, it's telling us that an HI just goes to one HI. It doesn't go to multiple HIs. Any questions on this? Okay, so we'll spend some time on the proof, and the proof is going to use this analysis. Okay. Good. I'm going to just take this off before I mess my jacket up. Okay, so let's prove this. Okay, so again, here's a setup. Let lambda be an F, mu in the closure of the set. Okay. Now, what does this say? Well, this says that if I take the stabilizer WP on lambda, it's contained inside the stabilizer of WP on mu. Okay, so I mean, just look at this picture, for example. The stabilizer here is empty, which is the identity. Here, the stabilizer includes the identity and also this reflection across this wall. Okay, so I mean, you can see from the picture this is true, and it's true in general too. All right. Now, we need to go back to the previous, so back to the previous technical lemma. And we also had a theorem which told us what happens with the translation. So, a character formula for translation from this lambda to mu. Okay. So we had a formula for actually doing this. And the formula involved looking at, you look at W1s inside the stabilizer, WP of lambda, mod the stabilizer, WP of lambda, intersection the stabilizer, WP of mu. Okay. Now, because of this, what happens? Well, this quotient is just gonna, this bottom thing is gonna be actually equal to the top thing, right? So you basically just have one element. So W is basically equal to identity. W1 is equal to. All right, so then what you have to do is you have to go back over this formula again, right? And so the consequences of this is as follows. So there exists one value, 1L, such that Just write it up and try to explain this. W dot lambda plus L, oh, sorry, lambda L is in WP dot V. Okay, so I sort of have to explain this. So remember that this is a weight of L nu 1. Okay? And the point is that the only, so if this is true, then this has to be conjugate to this weight nu 1 up here. And if it's not, if it's sort of smaller and conjugate, then this cannot happen. That's by this technical lemma. Okay? So this definitely has to be a conjugate of nu 1. And then how do we express the conjugates of nu 1? We express them in terms of these elements over here. And there's only one such one you can do, basically. That's a little exercise. And so that's why there's only one of these which actually lives inside. Well, that's good news because I can erase this. So now we're almost there. So you look back in this short exact sequence. So remember we have this sequence PR new, HI of MJ. Let's see. Just want to make sure I got this correct. Okay, index to a J minus 1 here. Let's see. Oh, J minus 1. So PR new HI of MJ and PR new of HI MJ over MJ minus 1. Okay. So remember that this one is lambda J plus W lambda, right? And so only one of these is going to light up, right? Well, only one of these is going to light up over here. So you have zeros except for in one position. So as a consequence, if I take PR mu of HI of MJ, this is going to be 0 for J less than L. So you can sort of run everything back to the beginning and actually show that this is true. Okay. And what happens for J bigger than L? For the only non-zero spot for which this is 0. So then HI of MJ is equal to HI of W dot. Okay, so for all J bigger than this. So it's a little exercise that you can do using long exact sequences to actually show this. All right. Well, this is kind of good news because I can set J to VR. Okay. And then I could just use the result I stated before. So what does that say? That says that T lambda mu of HI of W dot lambda, which is equal to PR mu HI J MR. And then by this is equal to HI. Okay, so that does the job. Okay, any questions on this? All right, now there are a bunch of other theorems which you can work out too. So, but I'm not going to prove all of them. Actually, I'm not going to prove any more of them. But they kind of have the same flavor as this. You have to analyze this long exact sequence, and then you have to kind of, pick out the right terms and so forth and so on. So I just want to kind of make a compendium now on what actually happens with translations with various modules. Okay. All right, so here's the next result. So proposition. Okay. All right, now, one question you might want to ask, let me just draw a picture over here to motivate this next result. So I'll draw two pictures. So here's one picture over here. Okay. So let's say I'm up somewhere in the dominant region, and I take some W dot lambda over here. Okay. So I want to. So lambda is in CZ, and let's say. Well, let me say it this way: lambda is in far, and mu is just on the interior. So, so the question is, what happens when I translate off a wall? So I want to know what happens to translation from lambda to mu of H0 of W dot. Okay, so I'm actually going off the wall. And what happens is it only has two factors of H0 in this case. So you get something up here and something over here. Okay. So this has a filtration. With factors. And these factors are, let's call them W1 dot mu and W2 dot mu. So they're the ones where you sort of blow things kind of off the wall like this. So it's H0. 1 dot mu and H0 W2 dot. So in particular, this module has good filtration. Okay. All right, so now suppose I take the Steinberg weight. Well, let me just do it over here. So let's say I'm at something like this. Okay. So I'm somewhere up here. Right? And so let's say I take my lambda to be this weight over here at the vertex. Okay. And let's say I translate into the alcove. Okay. So lambda is at the vertex. Let's say W lambda is at the vertex. And let's say mu is in the interior. It could be sort of very far in. So then what you do is you kind of look at the action around the vertex. So you're looking at this way, this way, this way, this way, this way. And so this translation, well, in this case, I have 6 composition factors. 6 0 factors. And the factors correspond to the weights around the vertex. Okay, so as you can see, if you're going off the wall or from vertex into like an alcove, then your translations get much more difficult. All right, so let me state this more precisely in this form. So again, let lambda mu be in the bottom alcove. And let's say W is in the alkaline vinyl group. And let's pretend that your weight is dominant. So, you know, I'm assuming that I have a dominant weight here, and let's say dominant weight over here. Okay. So then, when I translate T lambda mu of H0 W dot lambda, this has a filtration good filtration with factors R, H0, W, W1 dot mu. Okay. Where W1 is in the stabilizer. Okay, we'll look at the pictures in a second. Okay. And each let's see. So each of these terms, of these factors, occurs at most one time. Okay. All right, so let's look at this picture over here. All right, so first of all, you know, what's in the stabilizer? Well, it turns out the stabilizer is just going to be a reflection over here. So basically, I can rewrite these things as W1 mu is equal to W1 mu. Sorry, let me just say it this way. Is equal to W. And one of them is going to be WS dot. One or the other, sort of depends on your position. Okay, so this is W2 dot. Okay, and S is the reflection across this wall. Now, similarly, what's the stabilizer over here? Well, it's going to be some subgroup of order 6 in the volume, right? So then you just translate, you just sort of apply those 6 elements in the stabilizer to pre-W on this thing, and that's how you get the weights. Okay, and that's what this says over here. Okay, questions on this? Okay, so now let's look at irreducible modules. So going to a wall is not so bad. And coming off of a wall, that's where the big mystery is. Okay. All right, so I have to kind of explain this again. See which one I want to use. I guess I'll use this one. Okay, so here's another proposition. So, you know, all these works sort of need explanation. All right, so let lambda and mu, the assumption is always the same. We always start at the bottom alcove by convention. And then I want to let mu be in closure of F1. Yeah. Let's see what I want to say. Okay, so let me just say this. All right, let this be in the closure of CZ. And then let mu be in CZ itself. Actually, what I want is I want this a little bit more general because I want to do this for any facet. So let me just say it's in a certain facet. And it's in, let me call this F1 here. So meaning that it's in a facet in CZ bar. And let's make that F1 bar. So, you know, the bottom alcove could look, you know, like very, very complicated, especially for, you know, higher rank groups. Okay. Okay, so let F be the facet. So I'm going to just take it to be the facet sort of obtained by just taking F1 and getting up to lambda, containing W dot lambda. So that the following happens. So if I take T lambda mu on the irreducible representation corresponding to W dot lambda, then one of two things happens. So it's either it's going to remain irreducible. Nice. As long as W dot mu, well, we need something stronger than just being in the closure of the facet. We need it to be in the upper closure. So remember, I defined the upper closure before. So this is the upper closure. Okay, so remember, a facet is given by a bunch of inequalities, right? And when you take the upper closure, what you're doing is you're taking the top inequality and making it an equality. Okay. So we defined that before. And it's 0 if W dot mu is not in the upper closure. All right, any questions on this? So, yeah, we draw a picture. You can almost, let's even do it for the bottom alcove. I think that's kind of illustrative. Sorry, okay, so we'll stick to this. It's a little bit, we're doing this for A2 all the time, but I could draw a B2 picture if I want. So. All right, so let's say I start with lambda here, okay? Let's pretend mu is over here, okay? Now, let's just look at the case where W is the identity. Right? So if I translate this thing here, so if I do my mu over here, why this thing is not dominant anymore. Right? So this thing is going to be 0. And so that's because the mu is not in the upper closure. If you're over here, same thing happens. But if you're right here, you're good, right? And that's the upper closure in this case. So that's kind of a picture. Now, the upper closure can kind of change depending on how you go up. So you kind of have to keep track of the upper closure. So let me just say, in this case, you get 0. But if you do translation where you've picked the mu to be here and the lambda to be there. So here mu is in CZ upper closure. Okay. So that means that T lambda mu of L lambda. So I think this situation sort of at the bottom kind of gives you a feel for why you need to sort of consider the upper closure instead of just going to any facet you want. Or any sort of, if you're in a closure, it's not going to necessarily be non-zero. Okay, questions on this? All right. Now, what happens when you translate an irreducible off the wall. Now, even in the case where you have a codimension 1 wall over here, it turns out that the situation is quite complicated. And the answer is still unknown. If we knew the answer, we would know how to calculate characters of irreducible representations. Okay, so let me set this up. Okay, so big question. What happens to L W lambda when you translate away from the wall? So we'd like to know that answer. Okay, so I need to actually say what a wall is first. So a wall is a facet. Facet F is called a wall. Okay. If and only if you take the number that's by 0 plus of F. Okay, so that condition is given by lambda plus rho. Alpha check is some power, some multiple of p. So there exists, sorry, wrong quantifier. There exists a unique alpha such that lambda plus rho alpha check is equal to m times p. Here I use n alpha times p, something like that. Okay, so for example, in this picture, this, like for example, is a wall. Okay, the vertex is not a wall because there you have more things which are multiples of p when I take alpha. Right? So let me. Okay, we're playing Kentucky, so this is not allowed. I probably used it too. So I hope they went. Okay, so here's the wall. Okay. This is the wall. Okay, so all right. Now let me just be a little more specific. So when you have a wall, you only have the stabilizer is just going to be the identity or one other element. Okay. So note, we can take, I'll call it S of F. This is going to be S beta NP. Okay. Where NP is equal to lambda plus rho beta check, right? So this element acts on the wall as the identity. Okay, so over here, your S beta or S of F is a reflection which goes across like this, right? It's going to act as identity on the wall. So I don't know, maybe I should draw a bigger picture. So let's say this is, I guess did I use lambda here? I use lambda here. Let me erase this lambda to make sure it's not confusing. Okay. All right, so the lambda here is now on this wall, and your S of F is going to be the reflection, which takes things on one side of the wall to the other side of the wall. And so the stabilizer of this F is going to be you the identity and just S it out. Okay, is this clear? What we're doing? Okay. It's good. Okay, so I think say this. All right, so now I can state what happens. Okay, so consider the following situation. So here I have, I mean, this may not be the bottom alpha. Okay, this could be some alpha. So you take this W mu there, okay, and so this is going to lie on this F, and so F is a wall. Okay, and so an S of F is going to be this reflection like this. And so what I want to do is I want to consider, so this is a proposition. I want to consider what happens when I take an irreducible representation whose weight is on a wall. And if I take the corresponding irreducible representation, and if I look at what it's, how many times that appears in there, can I say anything? And the answer is yes. And the answer is 2. Okay. So it appears in the head and it appears in the socket. So that's another thing I could say. So this can be proved. So it appears at the bottom of this module and it appears at the top. And it's also equal to T mu lambda modulo rad. Okay. All right, so let me kind of draw a picture. Okay, so here's a picture of what's going on. So I'm looking at this module, LW. Okay, so at the top, I have LW dot lambda. At the bottom, I have LW dot lambda. And it turns out that I have some stuff in between. Okay, so the stuff in between, so there was a joke a long time ago, it was called the Janssen middle. Right? And Janssen's a really robust person. And so at conferences, people were saying, making a joke, that the Janssen middle is getting bigger and bigger. All right, it wasn't a very kind joke, okay? So I apologize to Janssen, he's ever out there. But anyway, another term that people call this is they call it the heart. That's sort of like the heart, right? Here's the head, here's the feet down here. And so the question is the heart semi-simple in various cases? And if it is, the list of conjecture is actually true. Okay. So the big problem, and we'll get into this in more detail, is to actually, one, determine if the heart is semi-simple. So when is heart semi-simple? Now, if, let's say, listed conjecture is true in certain cases, then it actually will be semi-simple. And if it's semi-simple, then the listed conjecture will be true. Okay, and then, of course, is to actually determine the composition factors in the heart. And in some sense, because, I mean, in some sense, what you're doing is this is kind of a recursive procedure because you can sort of go down to things that you know from smaller algebraic groups. You know? So, or smaller root systems. So the thing is, the point is that if you knew how to determine the composition factors of the heart too, you would also be able to solve with the characters of the irreducible type. So this is still an open problem. Not much is still known about it. And so, I sort of encourage you, if you're interested, to kind of, think about these sort of things. All right, we'll talk about more of this on Monday. And then after Monday, actually, probably after next week, what we'll do is we'll talk about GRT modules a little bit. And then we'll talk about injective G modules and GRT modules. And we link those to tilted modules. Okay, so let me stop there.
Has anyone answered either one of those questions for special cases?
No, I think for low rank cases you can do this, but in general, it's still, because of Jordan's counterexamples too. This problem.
So you have this like the